Hey all, this is Derek, and this is section 9.3, exponential functions. So we just left inverse functions, and what we found was that the domain and range of a function and its inverse are swapped. And for the rest of this chapter, we'll be looking at exponential and logarithmic functions, and those two functions are inverse to one another. So in this section, we'll look at exponentials, and we'll look at logs next, and then we'll be able to see that inverse relationship between the two. Okay, so exponential functions, transformations work the same on these as they do for all of our other functions. The one thing that's a little bit different with an exponential is the base can change, so we don't have a particular parent function, but we do have, cat invasion. We have sort of more of a family of parent functions. For exponentials, they're going to take the form y or f of x equals b raised to the x. The base will be constant. The exponent is the counter. That's the thing that's changing. B has to be greater than 0 and not equal to 1, because then it would be boring if it were equal to 1. Let me graph one of these, and then the asymptotes and domain and range will make a little bit more sense. So for graphing an exponential, at least the parent function, -1, 0, 1 give you a good 3 points to look at. If I only put in 0 and 1, 5 to the 0 would be 1. Anything to the 0 is 1. 5 to the 1 would be 5. And so if I only put in those 2 points, when x is 0, y is 1, and when x is 1, y is 5, it could be anything, right? And so I need at least one more point to kind of get a sense of what's going on. With this -1, 5 to the -1 would be 1 over 5 or 1/5. And then you can kind of see what the behavior is going to do. If I put in -2, it would be 1/25, -3, 1 over 125. So this side's going to get really close to 0, but never actually get there. It's going to have a y-intercept if there's no stretch at 0, 1 every time, because when x is 0, anything to the 0, it becomes 1, unless there's a multiplier in front. And then when this was 1, this was 5, but if this was 2, this would be all the way up here at like 25, way off the graph. So you can see these things go to 0, and then they get very, very large very quickly. And so that's kind of our behavior for exponentials if they haven't been flipped around or anything like that. And we'll see we can do all the same transformations on these as we saw earlier in the course with the other functions. For our domain for exponentials, this is going to be all real numbers every time. Our range without a translation is going to be from 0 to infinity, and we're not including that 0 because we can only get closer and closer to it but never actually touch. And then our horizontal asymptote is right here, and it's the x-axis, but remember that that is y equals 0 because all of the y's are 0. X can be any value. Y is neither above nor below. It is constantly 0. So that's an example of a basic parent function. So when we go to do transformations on these, we'll have to think of this one, and then the same, right, left, up, down, reflect, all that same stuff is still going to apply, but now with a new function. Okay, for this next one, we're starting off with the same function I just graphed on the last page. Our basic one here is y equals 5 to the x. For this first one, it's y equals 5 to the x, but then a +3, and that +3 is on the end, or like the outside, and so that's going to be our up-down shift. So what it would do is it would just take the one that we drew last time, and it would just bring everything up 3 units. So for graphing on the computer, you only need to graph 2 points, and so this one down here that's a fraction is not going to be one you're going to graph. So you're going to graph those 2 right there, and then the computer will draw in the rest for you. And then this one with this +3, you can see it would have had a horizontal asymptote that also moved up 3 right along with the function. The next one, this is, let me write that a little bit bigger because that exponent's super small. So this one has a -2 up in the exponent, so that would be like on the inside of the function. So this is what our left-right looks like, and then this is our outside, this is our up-down. So minus would go right, another cat invasion. And so we'll just take the parent function here in black and go move everything right too. So we'll just do here and here. And so that's an example of a horizontal transformation. These next two are our reflections, and this time it's a base 3 instead of a base 5. So if I'm making that same little table, -1, 0, 1, I would get, and this is for y equals 3 to the x, 3 to the -1 would be 1/3, 3 to the 0 is 1, and then 3 to the 1 would be 3. And again, the computer is going to draw this for you, but you do have to figure out at least kind of where these base points are. And so on the computer, that's what you would need to draw. Not that you're drawing the parent function, we're going to draw the reflection, but putting those 2 points in would have it draw that for you. And then that last point would be that 1/3 on paper. So this one is, write it a little bit bigger, y equals 3 to the -x. So that's a negative on the inside, so that's going to reflect across y. So this point just swings over here. You can kind of think of that as a hinge. And then we're right like that. This is also the same thing as, remember, if we have a negative exponent, this could be 1/3 to the x. And then since that numerator is 1, I could write that as 1/3 to the x. And then this becomes what's called exponential decay. And this one is exponential growth. So this is getting smaller, right? This one's getting bigger. This one over here, again, let me just write it a little bit bigger just so you can see. This one has the negative in front. So to kind of keep these two straight in my head, when I was a student, I always would think of -x squared and go, okay, that's the one that reflects down. So this is the one that would reflect down. So again, we'll take the parent function in black, and we're basically like folding that across the axis. And it looks just like that. Okay, and so then these next ones are just kind of combinations. So let me write this a little bit larger. Y equals 3x minus 4 plus 3. So this is like y equals 3 to the x again. So our parent one, I'm just going to kind of sketch in there so I have it to reference. And then we are going to go, let's see, we're going to go -4, so that would be right 4, and then up 3. And so one thing I like to do if I'm drawing it on paper, which you can't do on the computer, but you can kind of at least count the boxes, is if it's going up 3, and I think some of the ones on the computer do draw in an asymptote for you, but definitely if I'm doing it on paper, I like to draw in the asymptote just because it kind of gives me a reference line and I'm less likely to miscount. So this is great. And also we're going to have to find our horizontal asymptote down here as well. So if I'm going to go right 4 and up 3, I could just take this point and go up 3 and right 1, 2, 3, 4. And again, up 3 and right 1, 2, 3, 4. And so if I just get those 2 points moved, again, the computer will draw in the rest. For our domain, that's going to still be -infinity to infinity always. Range has moved up with that vertical shift. And so that's going to be from, oops, not 0, from 3 to infinity. And our horizontal asymptote also moved up 3. This next one, let's see, this is -5x plus 4. Y equals. And so the 5 would be through 1 and 5, right? Because it always goes through 0, 1, and then through 5, because it's a base 5. 5 to the first would be 5. So there's our parent function. That negative in front, that's going to flip it upside down. So that would put it down here. So that takes care of that piece. But then that plus 4 is going to move it left 4. And so then I can just take this picture and move everything left 4 units. Domain, all real. Range, this time it's going from -infinity up to, not including 0. Horizontal asymptote, still y equals 0. Just now it's approaching from the bottom instead of the top. Okay, so this one we got 4x minus 2 and then -5. So that's going to be right 2, and then down 5. And then this is base 4, so it would go through when x would be 1, or when x is 0, y is, when x is 0, y is 1, and when x would be, let me write it out. So when x is 0, y is 1, and when x is 1, y would be 4. So that's what I'm doing every time, just to kind of get those initial 2 points, and then those are what I'm moving around. So we said right 2, so right 2 and down 5, put this one here. Right 2 and down 5 is right there. Since this shifted down 5, that means my new asymptote is right there. And that would be where my graph would be. So domain still negative infinity to infinity. Range is now from -5 to infinity, and our horizontal asymptote always comes off our range. Y equals -5. Okay, so next we're trying to find the equation of an exponential given either point and intercept or 2 points. And we're going to see a couple of different versions of the same thing, just a few different notations, or depending on how we're presented with the information. So for an exponential, we have f of x or y equals ab to the x. So this time we're just including the possibility of a stretch factor that's not 1. And in the ones we were just graphing, we just assumed a stretch factor, or we only looked at cases where the stretch factor is 1. And then this b, this base, this will be a growth factor or a decay factor depending on the sign of the rate. But the b in this formula is the exact same thing as the r plus 1 in this formula. So the same formula, a is going to be, it's going to turn out to be our initial value. Because if we think about something like y equals 5 times 3 to the x, if x is 0, this piece becomes 1, and then 5 is our initial value. So this is going to be our y-intercept. B, again, growth factor, or also decay if it's negative, is a rate plus 1. And you'll see we start getting some percentages in some of these problems. That's where we're going to use that. And then R is a percent growth or decay, as I was just saying. So let me show you how this looks with examples. This first one goes, find the exponential function of that form. And this one is saying f of x equals a to the x. So this is kind of one step back from this problem, kind of back to the ones where we just were, and they'll get a little bit more complicated on the next example. So this one has a leading coefficient of 1, so what we're really solving for is what I was calling b up here. Anyhow, so find the exponential function of this form that passes through the point -225, has a y-intercept of 1. So if my y-intercept is at 1, that means I have x is 0 and y is 1, and that is a. And so if we're in this form, we just kind of showed that this part right here is 1, and now we're solving for b. Again, they called it a in this problem. So that's an x and a y. So if I think of this as y equals a, I really wish that you called that b, to the x, then 25 equals a to the -2. And then solving that, I can go, I think I will drop that down. And then I'm going to multiply this side up. So it'll give me 25a squared equals 1. And then divide out the 25. 1 over 25. And then I can root both sides. And I'm going to not do a plus or minus there because this is the base of an exponential. And the base of an exponential has to be that greater than 0, not 1. So this would be a is 1/5. And so to write my answer, this will be y equals 1/5 x. Okay, and now the rest of these are going to use that same notation that I was using, which is y equals a b to the x, where a is our initial value. So for this one, we're given these 2 points, 0, 100. Well, when x is 0, y is 100, that's great. That is our initial value. So now we know that a is 100. And you can see if I put in, just to kind of show it one more time, if I solve for y is 100 equals AB when x is 0. B to the 0 is 1. And so that's just showing that A is 100. We don't have to go through all that, but that's why that worked. And then this is an XY right here. And so now that I know A, I can solve for B because I have another XY to plug in. So letting Y be the 21,600, and then A is going to be the 100 we just found, and then B is what we're trying to work out, and X is 3. Now I can solve for B. So divide over the 100. And that's going to leave 216 equals B cubed. And then I can cube root both sides. And cube root of 216 is 6. So now my equation will be y equals A was 100 times 6 to the x. Okay, so for number 9, we are not given the y-intercept, which means we're not given A. So that means we're actually going to get a system of equations. So let me show you what that will look like. And again, we are using y equals AB to the x. That's kind of our template. And this is an xy, as is this. So we'll set up two equations with these x's and y's. So first one's going to go 10 equals AB to the x is 3. And second one's going to go 160 equals AB, and then in that case x was 5. So what I want to do, there's a couple of things I could do. I could solve these both for A, set them equal. I think I'm actually going to do a substitution because I think it's going to save me a step. So I'm going to solve this one for A and then substitute it into there. So let's divide the B cubed on both sides to get A by itself. And then I have 10 over B cubed equals A. Once I have that, now I could take this expression that equals A and plug it in right here. So that's going to give me 160 equals 10 B cubed times B to the 5th. And now we have B to the 5th over B cubed. So that's going to leave a B squared. So 160, 10B squared. We'll divide out the 10. So 16 equals B squared. Remember, B has to be a positive number, so B is 4. So there's our first of our two values. I'm going to just take this and I'm going to drop it, might as well do right there, because that's going to get me A, which is the other thing I need. So 10 and then 4 cubed will equal A, so that's 10 over 64, which is 2 goes in 5 and 2 goes in 32. So A is 5/32. So for this one, it's a little messier, but y equals 5/32 times B is 4 raised to the x. Okay, and then last we have finding an exponential function for an application. So here we have a population numbers 15,000 organisms initially and is decreasing, so going down by 6.7% each year. Suppose P represents the population and T is the number of years of growth, in this case decay, or negative growth. So write an exponential model for the population. So P equals, remember A is our initial value, so that is 15,000, because that's how many of these little critters we are starting with, whatever they might be. And then if you remember on this page back here, grab that. So we have this formula, this R plus 1, that's what I'm going to use right here. So rate, this is decreasing, so it's going to be negative 0.067 plus 1. And that is raised to there using T as the variable there. And then combining those two, just to simplify a little bit, 15,000, and that'll be 0.933 T. And so if the B can't be 1, because if it's 1, it just keeps being 1 no matter what you raise it to, so it's not very interesting. If it's between 0 and 1, you're going to get a situation where the population is going down. If it's greater than 1, you're going to get a situation the population is going up. So that's that decay versus growth. And for this one, that was all they wanted. So here we have the fox population in a certain region has an annual growth rate of 9% per year. It's estimated that in year 2000, the population was 28,200. A, find a function that models the population t after t years after 2000. So in other words, we're going to let this be t equals 0. So at t equals 0, we know our population is 28,200. So that means we are doing p of t, I think was how they had this one, equals the 28,200. And then this one's going to be our 9% per year, that's 0.09. So this one will be that plus 1, and this is growth, so it's positive, so I'll make it 1.09, and then to the t. And then part B is use the function from part A, this, to estimate the fox population in 2008. So 2008 would be t equals 8, so we're just going to find p of 8 and plug 8 on into this equation. And then that came out 56,190 foxes. And I think we're supposed to round to the nearest fox because we shouldn't have fractional foxes.